General relativity, step by step. The first thing I'm going to do is correct an error which I made at the very end of last screencast. I didn't want to record the whole thing again. Get rid of that 0 there. What I'm doing in either of these cases, I'm considering the limit as r0 approaches infinity of r0, let's take this one, sine r over r0, equals the limit as r0 approaches infinity of r0 times, and then sine is r over r0 minus a sixth, I think it is, r over r0 cubed, higher terms there. Put a bracket there. So of course what I'm going to do is to neglect the higher order terms and then observe that the r0's cancel, equals r. And so this solution here, this third one here, is just the limit, and of course I could have put hyperbolic sign in there for the first one, except that the sign would change. This is a limit as r0, this is a limiting case. The limiting case of flat space, I guess. So I'm going to delete that. Delete. Right, I'm going to consider this one here, the k is less than 0 solution. So what I'm going to do is I'm going to write out the full metric. I'll see if I can find it. It's up here somewhere. It's quite a long way back in history. I'll find it eventually though. Oh dear, quite a long way. Quite a long way. What the hell? Oh dear. Oh, here it is. This'll do. There we go. So I'm going to write out that metric there. But now I know what Q is. So I'm going to write it in and we'll play with it and see what it tells us about the universe. Oh dear. Still going. Here we go. Right. So let me just pinch in a little bit. ds squared equals minus dt squared plus a of t squared times dr squared plus, and now I can substitute for q, r0 squared sine squared r over r0, remember I'm doing this term here, I'm doing the k less than 0 term, times d theta squared plus sine squared theta d phi squared. Close curly brackets, and I think I opened a bracket there. Now again, what I'm going to do is take Kip Thorne's advice again, which is incredibly profound advice. I can't say this often enough. We're going to consider one simplification after another. So what we're going to do is take this rather complicated beast here, and I'm going to simplify it. So what I'm going to do is I'm going to consider theta equals 90 degrees, I guess. There we go. And I'm also going to consider a fixed moment in time. Just because I can. That'll make my life easier. So I'll say that ds squared equals, and then this term is gone, that term's gone. A of t squared times dr squared plus r0 sine squared r over r0. And then of course this tells me that d theta equals 0. So I can ignore this term as well. I'm ignoring that term and that term. So we're considering two simplifications simultaneously: fixed moment in time and also sort of an equatorial assumption here with theta equals pi by 2. Okay, so we've got r0 squared sine squared r over r0, which is there. And of course, sine squared theta is just equal to 1 because sine of 90 degrees equals 1. So that just becomes a d phi squared. Close those. That's quite nice, isn't it? Let me just reorient this. I'm going to express it in a slightly different way. I'm going to define this new chi, this new variable chi, and that's going to equal r upon r0. So that's a new variable chi. It's just a linear transformation, but we'll see that it makes life very much more clear to us. So then ds squared equals A, I don't need to write the functional dependence of A here because I'm considering a fixed moment in time. So I'm just going to write A. Oh, it's going to be A squared, I guess. Times dr squared. Well, that's just, there's a squared there. That's going to be r0 squared d chi squared plus r0 squared sine squared chi d phi squared. That's nice. Equals r0a squared d chi squared plus, actually I'll put that in brackets there, let me just rewrite that a bit more neatly, chi squared plus the r0's come out, the a's there anyway, sine squared chi d phi squared. Right. Now we've seen this before. This is, it's not like, it is the metric on the surface of a two-dimensional sphere. So I'm going to try and draw this. We've got our sphere, we've got our sort of lines of equal latitude, we've got a north pole and a south pole, we've got this kind of angle in here which I've called, in this case I'm going to call that angle chi. Normally you use a different letter for that. And we've got the azimuthal angle going around here called phi. That's not a very good phi, is it? That angle going around in this direction is phi. So that's just the same as the surface of a sphere. So what we're saying, just observe that the sphere is a nice surface and it's got a nice constant curvature. We're saying that this solution here, where our variable k was negative, corresponds to a solution to the Einstein field equations with constant curvature exactly in the same way that a sphere has got a constant curvature. And we call this a closed, could put it in scare quotes, a closed universe. There's just a couple of notes of caution here. Just because it's like a sphere embedded in a higher dimensional space doesn't mean that the global topology of the universe is as I have just described. The Einstein field equations specify local properties. Can't even write it, properties. Things like local curvature, things like black holes and so forth. It describes local properties. The Einstein field equations are silent on global topology. They do not talk about global topology at all. And I'm going to stop the screencast right now because it's already gone on too long. What I'm going to do in the next screencast is talk about the relationship between global topology and local properties, and I'm going to talk about that in terms of familiar things like toruses and spheres. But for the moment I'm just going to stop here. We've got this nice solution that in some sense this plane here of theta equals 0 is a sphere, but a sphere is a topological object as well as a geometrical object, and the Einstein field equations are geometric restrictions on our space-time, not global topological restrictions. Stop.